Hello, I am Banashree Saikia. I am going to talk about laser and its principle. From the acronym itself, laser is light amplification by stimulated emission of radiation. That is, light should be amplified, and it is by the process of stimulated emission, which is predicted by Einstein in 1917. The phenomenon of stimulated emission, first used by Tanuj in 1954 in the construction of maser, that is, microwave amplification by stimulated emission of radiation. The maser principle was later extended to the optical frequencies by Swallow and Tanuj in 1958. The first successful operation of the laser device was demonstrated by Meyman in 1960. The essential ingredients for the fabrications of laser can be adequately described by the consideration of the interaction of radiation of matter. There are three types of processes involved in lasering action, namely stimulated absorption, spontaneous emission, and stimulated emission. So we'll discuss one by one. First, stimulated absorption. An atom has a number of quantized energy states. Initially, an atom is in ground state, that is, all of its electron possesses lowest possible energy state. When energy h nu is given to an atom, it goes to excited state, that is, its electron jumps to higher energy state by absorbing a quantum of radiation or photon. The process is called the absorption of radiation. Suppose E1 is the lower energy state and E2 is the higher energy state. If a quantum of radiation h nu is incident on the electron which is in the ground state, then it will absorb energy h nu and goes to the high energy state E2, where nu is the frequency of radiation which is incidence on this atom. Therefore, the energy difference E2 minus E1 is equal to h nu. Since electron is initially at ground state, that is A, and by absorbing energy h nu, it goes to the higher energy state, that is S star. Therefore, the equation we can write it as A plus h nu tends to S star. The probable rate R12, the transition from 1 to 2, mainly depends on the energy density rho nu and the number of atoms present in the lower level. That is, R12 is equal to B12 N1 rho nu, where B12 is the Einstein B coefficient for the transition from 1 to 2. Next, spontaneous emission. In case of spontaneous emission, the electron is in excited state and excited electron is not stable. It can remain in excited state only for 10 raised to minus 8 seconds. It then, of its own record, jumps to lower energy state by releasing a photon of energy h nu, which is exactly equal to the energy difference E2 minus E1. Therefore, we can write it as the S star tends to A plus h nu. That energy is released in the emission process. The probable rate R21, that is the transition from 2 to 1 is mainly depends on the number of atoms present in the higher energy state. Here, this A to 1 is the Einstein A coefficient for the transition from 2 to 1. Next, stimulated emission. In case of stimulated emission, there are certain excited states where electrons can stay there for around 10 raised to minus 3 seconds. These states are called metastable states. Suppose electron of energy h nu is in the excited state. If one photon of energy h nu E2 minus E1 triggers the electron to make downward transition, emitting an additional photon of same frequency. Thus, there are two frequencies of same frequencies of two photons are released. This phenomenon is known as stimulated emission process. In this case, that the A star, which is for the higher energy state, plus the incident energy h nu tends to A plus 2h nu. Therefore, the quantum of photon that is released is twice the incident photon. That means it is amplified. Therefore, the rate of transition for stimulated emission from 2 to 1, that is mainly depends on the number of atoms in the high energy state and the energy density which is incident on the excited photon. And B is the Einstein B coefficient for the transition from 2 to 1. Thus, we have discussed all these three transitions which is involved in lasing actions. Thank you.